So our very first section is going to be about angles. You have seen these at some point in your life before. We're just going to define them more formally. So in general, an angle is formed by intersecting two rays at a common endpoint called the vertex. Okay. So we're going to draw some pictures. A ray is basically you have a starting point and then you have a never-ending line going off of it in one direction. So this here is a ray. The point where it starts right here is called the vertex. Okay. So an angle is formed when we position two of these so that they have that same starting point. So we have a common vertex. We have some initial side to our angle. And then what happens is we just rotate this around until it ends at a different side. So we have another portion off of it. Okay? So in this case, this particular angle was formed by rotating it in the counterclockwise direction. We're often going to use Greek letters to represent our angles. So the most common one is theta, but another one you'll see often is alpha. Okay? So this first ray here is our initial side. And then where that ray ends is called the terminal side. So this case, when we move in a counterclockwise direction, we have a positive angle. So we work a little backwards in math. If you move the opposite direction, which is clockwise, that's going to result in a negative angle. So maybe I still have the same initial side, but now I'm going to go ahead and I'm going to move downwards and rotate that down. So I really could have exactly the same picture, and there's two different angles that are represented here. So in this case, I've gone clockwise. So I'll call this one beta, which is another Greek letter, but this represents a negative angle. So because we're really moving in a circular motion, we have a lot of repeat positions. It just depends on how many rotations. But remember, one complete rotation around a circle is going to be 360 degrees. And in that case, that would be you go one full time around, and your terminal side and initial side are exactly the same. So in general, 1 degree is going to be 1/360th of a rotation. So this is how those degrees were defined. We have some special names for angles as well. So we're going to look at 4 different ones. We have right angles, straight angles, acute angles, and obtuse angles. A right angle is one that forms a 90-degree angle. So this is one you are used to, but this angle here is 90 degrees. So we often use that box to represent it. So if we go in that counterclockwise direction, this would be our angle. And again, we like to use theta. So for a right angle, this will be 90 degrees, which is just like all the angles in your rectangles and squares. A straight angle is still going to have some initial side, but now what's going to happen is you form a straight line with the terminal side. So if this is our angle theta, in this case, a straight angle will be 180 degrees, which is half of a circle. An acute angle and obtuse angle just represent a range. Acute, I like to think of tiny cute animals. So these are smaller angles. So it's something smaller than a right angle. So get a smaller highlighter to fit in here a little bit better. But if this is our angle theta, theta is going to be bigger than 0 degrees, but less than 90 degrees. If we have an obtuse angle, if here is our initial side, obtuse is something that's a little bit bigger. So when you go for that angle, it's going to go past 90 degrees, but it's going to be smaller than a straight angle. So if this is theta, theta is going to be bigger than 90 degrees, but less than 180. So typically we don't really care about angles past that. The ones between 0 and 180 are the most essential just in this context, because if you have an angle that's bigger than a straight angle, then really you always have a smaller angle that corresponds to it as well. When we talk about this in terms of the XY planes, then absolutely larger angles are going to be essential to us, and we'll figure out how to work with those. But now if we're talking about two angles in conjunction with each other, we say two angles, alpha and beta, are complementary. If those two angles add up to 90 degrees. Instead, we say they are supplementary if those two angles add up to 180 degrees. Okay. So let's try a quick example of this. We're going to find the complement and supplement of 71 degrees. So starting with the complement, if I have some angle x with this angle of 71 degrees, their sum needs to be 90 degrees. So solving for x, we just need to move the 71 to the other side. So we go ahead and subtract it. So the complement of 71 degrees will be 19 degrees. And that's why I need a bigger highlighter tool. Let's switch back to it now. Okay, going for the supplement, if I take an angle y and add 71 to be supplementary, it needs to add to 180. So again, just moving the 71 to the other side by subtraction gives us our angle y has to be 109 degrees. So the supplement of 71 is 109. Okay? So again, you've likely worked with angles at some point in your life and you've seen them. However, what you probably haven't seen is an old way that traditionally we used to represent angles. So if I'm talking about a portion of an angle, so I don't make a full degree rotation, but you do move a little bit. In that case, degrees have been measured with what's called minutes and seconds. It comes from the ancient Babylonians because they used everything in coordinates with their time system, hence the minutes and seconds. So really, if I want to talk about a fraction of a degree, it's in terms of 60ths, because 60 minutes are a single hour, and then 60 seconds are a minute. So if I'm talking about a minute in terms of degrees, the way we write this is with a 1 and a single tick mark. This is 1/60 of a degree. But the easier way to think about this is if you have 60 minutes, that's equal to 1 degree. Okay? So 60 minutes make up a single degree, so I can break down a degree into smaller pieces. When we then talk about seconds, we're going to use 2 tick marks. This breaks the minutes down further. So it breaks the minutes into 60 parts, which really, because a minute breaks down a degree into 60 parts, this is 1/60 squared of a degree, or 1/3600th of a degree. Okay. But again, the easier way to think of this is just like time. If you have 60 seconds, that's equal to 1 minute. So 3,600 seconds, when you times both by 60, would be 60 minutes, which in turn is 1 degree, okay? So just like there's 60 minutes in an hour, there's 3,600 seconds in 1 hour. So basically 1 hour is like our 1 degree. So if we want to convert back and forth between these, we just have to remember what each of those pieces is. So we're going to convert 74 degrees, 8 minutes, and 14 seconds to decimal degrees, and we're going to round to the nearest thousandth. Okay. So basically, I want to see what each of these are equal to in decimal form, right? So if I start with my second piece, this is going to be those minutes. So this is really just 8 minutes. Okay. That really, again, is representing 8 minutes out of an hour. So it is 8 times 1/60 of a degree, which really is just saying you have 8 out of 60 of a degree. Okay. So 8 minutes out of 60 for that 1 degree. The 14 seconds is really 14 out of how many seconds there are in an hour. So you take 14 and times it by the fact that there are 3,600 seconds in an hour. So 14 seconds is equivalent to 14 over 3,600 seconds. Okay. So if I'm looking at 74 degrees, 8 minutes, and 14 seconds, all I'm going to do is take 74 and I'm going to add these fractions, 8 over 60 plus 14 over 3,600. And these are all in degrees now. Okay. If you have 74 followed by those minutes and seconds should not be more than 1. So I'm going to trust you'd be able to plug these fractions into your calculator. This should give you about 74.137 degrees. Okay. So again, this stuff at the end should not equate to more than 1 degree, right? So let's go ahead and add 51 degrees, 29 minutes, plus 32 degrees, 46 minutes. So I'm just going to go ahead and write this like a standard addition. And you just go ahead and add those like components together. So if I start by going and adding those minutes together, 26 plus 46 is going to give me 75 minutes, okay? And then adding the degrees together, 51 degrees plus 32 degrees gives me 83 degrees, okay? Now you think this would be good, however, we do have a bit of a problem because just like time, 75 minutes is more than 1 degree. So you can think of breaking it down again, just like you would in terms of hours. 75 minutes is exactly the same thing as 1 hour and 15 minutes. So I'm breaking it down based on those 60ths, okay? So I do need to go through and I need to fix this piece here. So 60 degrees, remember, 60 minutes is 1 degree. So we need to fix this 75. 75 minutes can be broken down as 60 minutes plus 15 more minutes. So 75 minutes is the same thing as 1 degree and 15 minutes. Again, an hour and 15 minutes. So really what happens is my 83 gets bumped up a degree. So 83 degrees, 75 minutes is really going to be 83 degrees plus 1 degree, 15 minutes. Okay. So adding those together, it bumps that degree up to 84, and then we're left with 15 minutes, okay? So again, you're gonna see some applications here, but realistically, we're gonna work in standard degrees for the most part. This is just really essential when it comes to certain applications. So anything in boating, they still use the degrees, minutes, and stuff like that. So we'll see some applications with bearings later on with it. But for the most part, we're gonna stick to standard degrees, and then we'll also talk about another way we can measure angles later on, which is radians, okay? Now what we wanna do is we wanna give some solid math to this. So one thing we can always do is kind of impose this on the XY plane. So we say an angle is in standard position if its initial side is along the positive x-axis and its vertex is at the origin. If it happens to be that your terminal side lies on the x or y axis, we call that a quadrantal angle. Because basically it forms a quadrant, okay? And like I said, you can continue to rotate around as many times as you want, so you can always land in the same spot, but still have bigger angles or smaller angles. So we say two angles in standard position with the same terminal side are called coterminal angles. So let's take a look at some specific examples. We're going to graph them in standard position. So we have three angles, negative 90 degrees, 270 degrees, and 630. So for each of these, I'm going to go ahead and I'm going to draw an XY plane. And I'm going to cheat. And I'm just going to copy and paste this because I need to do three different ones, okay? So again, if you think about a full revolution, that is 360 degrees. So a straight angle is 180. And then each of these quadrants, they meet at right angles. So those form 90 degrees. So if I'm going negative 90 degrees, that's going to tell me I go in the opposite direction. So instead of going counterclockwise, the negative angle tells me to go clockwise. So my initial side is going to start here on the x-axis, and then I need to go down 90 degrees, and I'm going to end right here on the negative y-axis. So this is our angle. From here to here is negative 90 degrees. So this is a quadrantal angle. To go 270 degrees, again, we just kind of have to think about this. This would be 90, 180, and then down here lands me at 270. So again, I have the same starting position, and then to go 270 degrees, we get 90, 180, 270. And this would be where our angle ends. So the terminal side is right here. So it is also a quadrantal angle, and it really is going to be coterminal with negative 90 degrees. If you think about 630, well, that's bigger than 360 degrees. So again, you can think about this in terms of 90. This is 0 degrees. This would be 90. This would be 180. This would be 270. And then coming back up here gets me to 360. Well, I need to go past that, so I'm going to keep going up by 90 degrees. 360 plus 90 is 450 degrees. 450 plus 90 means this side over here is also 540 degrees. Adding 90 to that again lands me at 630 degrees, which is exactly my angle. So really 630 degrees is 360 degrees plus another 270. Okay. So I still start right here. And then to get this angle, I go around once, which is 360 degrees. And then I keep going again until I land right here. So my terminal side is exactly the same. So all three of these angles are quadrantal and they are coterminal. Okay. So again, I can do this a lot. I can always add 360 and I'm gonna land in the same spot. I can add 360 as many times as I want and go another revolution around and I'm going to land in the same spot, okay? So I could also do the opposite direction. I could subtract 360 to go the opposite direction, and I'm still going to land in the same spot. So you really have an infinite number of angles that are coterminal with each other. You just keep adding or subtracting one full revolution, okay? So let's try another example. Given that theta is 124 degrees, we're gonna find the measure of two other angles, one positive and one negative, that are coterminal with the angle and closer to the given angle than any other coterminal angle, okay? That basically means I want the smallest ones that are closer to it. So I only want to go one revolution in each direction. So my angle of 124 degrees, if I draw a little picture of what's going on, here's 0 degrees, 90 degrees, 180, 270, and then again we land back at 360. 124 degrees is somewhere in between here. I don't have an exact angle, but it's something like this, okay? So our angle theta would be 124 degrees. So I'm just gonna go one revolution in each way to find a positive coterminal angle and then to find a negative coterminal angle. So our positive coterminal angle that is closest to it is I take my ending point and I go one more revolution around. So 124 plus 360 would tell me one coterminal angle is 484 degrees. So this is the closest positive one. Okay. So again, that would just be found. You go one more direction around and land there. To find my negative coterminal angle, I go the opposite direction. So that means I subtract 360 degrees. 124 minus 360 gives me negative 236 degrees. So essentially from the starting point, I go backwards minus 360 degrees. So these are again two angles that are coterminal, but you could find much more. They are just the ones that are closest because they are a single revolution, okay? To then go into something a little bit different, now let's give an expression that generates all angles coterminal with a 120 degree angle. So here I want an expression that tells me every single angle coterminal with 120 degrees. So in this case, what I need to do is I need to basically find a way to represent how many full revolutions I'm going. So we can always add or subtract any multiple of 360. To get a coterminal angle. So typically what we do is we let n represent the number of revolutions that you're taking. So we use n to represent an integer. Which again is the number of full revolutions. Okay. So then all of my angles that are coterminal with 120 degrees is, we take our starting point and we add or subtract any multiple of 360 degrees. So n is telling us how many times. If n is 1, that's 1 revolution. So that gives you that positive case. And if n is -1, that tells you to go the opposite direction. That's the negative case. Okay? So I just got one more of these for now. We're going to find the angle of least positive measure that is coterminal with 4,777 degrees. So again, the least positive measure tells you it's within 1 revolution. So least positive measure means an angle between 0 degrees and 360 degrees. Okay. So all you're going to do is take 4,777 and subtract 360 a bunch of times. So keep subtracting revolutions until we get an angle in that range. Okay. So you can sit here with a calculator and you can take 4,777 degrees, subtract 360. Well, I'm going to have to subtract it a lot. So keep doing it, keep doing it, keep doing it. I'm going to tell you, you need to do that 13 times, okay? To be able to get something between 0 and 360. So basically we're going 13 revolutions backwards. So you're kind of using this formula here. We're replacing the 120 with 4,777. And I need to go the opposite direction to land back into something between 360. So in this case, when you do it 13 times, you can sit there 360 times 10. 360 times 10 would be 3,600. That still gives you like 1,100 degrees. So that's not quite right. Then you can try 11, 12. 12 still doesn't get you there. 13 finally will. So if you do 360 times 13, it would give you 4,680. And then finally subtracting these two gives you 97 degrees. And that is an angle between 360. So 4,777 degrees